Let me also say that if you would like to ask questions as I go, please feel free to, I guess you can type in the chat, and Ratnesh, maybe you could keep an eye and you can interrupt me if there are questions. It's no problem. Otherwise, hopefully plenty of time for some questions and discussion at the end. So first up, I want to say thank you for inviting me to be with you today, even if it is just virtually. I guess we're all getting used to doing these things virtually. It's really nice to have the chance, and I wanted to also take the chance to wish you congratulations and happy birthday. 75 years is quite an accomplishment, and I really enjoyed learning a little bit about the mechanical engineering department. So thank you for sending me the materials and learning a little bit about your history as well as your present. So before I launch into the technical presentation, I just want to acknowledge the people who work with me on the project, on the work that you're going to see. So first and foremost, this is Michael Kaptein. He's a PhD student. He's one of my MIT PhD students. And in fact, he's busy finishing up his thesis. He should be defending his thesis in just a few weeks' time. And most of what you're going to see today is Michael's PhD work. We also collaborate with Dr. David Knezevic, who is the CTO of Axelis. It's a startup company that does the reduced order modeling software that you'll see that we're using. Jacob Pretorius is CTO of Jasara. We work with Jacob on the experimental testbed. And then Stephanie Salinger is one of my master's students here at UT Austin, and Stephanie has contributed to some of the experimental work. So let me launch right in and start with the topic today, which is the concept of a digital twin. And I'm sure that many, if not all of you on the seminar today have heard of the idea of a digital twin, because it is something that's gaining a lot of attention in many different fields. So I have a definition up here on the slide. A digital twin is a set of virtual information constructs that mimics the structure, context, and behavior of an individual or a unique physical asset, is dynamically updated with data from its physical twin throughout its life cycle, and informs decisions that realize value. And this is a definition that is in an ARAA Institute position paper that was published last year. And it's a definition that kind of arose through a lot of discussions in the community and different definitions, different contributions. So, of course, definitions are always imperfect, but I think this is actually quite a good definition because it highlights to us what is a digital twin, and importantly, how is a digital twin different to just a simulation model that we as engineers have been using for many, many years. And so I want to call out three pieces. The first is that we see that the digital twin is tied to an individual or a unique physical asset. So that's sort of emphasizing the fact that this is not a generic model. This is not a generic model of a Boeing 777. It's a model of one particular Boeing 777, one tail number. And again, it's a model that's focused on the individual or the unique physical twin. The second element I want to call out is that this is not a static model. This is not a model that we create and then we're done, but rather it's dynamically updated and follows the physical twin, follows that unique physical asset throughout its life cycle. And then the third element is that a digital twin really informs decisions that realize value. And often it will be informing decisions that are made by a human. And I think one of the perhaps most exciting things about digital twins is that it has a potential for revolution, not just in one little piece of the system, not just in design or not just in operation, but it's something that really could impact and change the way we as engineers think about the life cycle, the entire life cycle of our systems. So clearly a digital twin potentially could change the way we design or even conceive of our systems in the first place. In particular, really thinking about the role of sensing and how at the same time we might architect the vehicle and its shape, we also think about architecting the information, the sensors, and the information that are going to follow the vehicle through its life cycle. So digital twin can change the way we think about design and conception. course, a digital twin can change manufacturing as a way to really harness all the incredible data that is now beginning to be available with modern manufacturing processes and use it for continuous improvement or quality control, or improving performance and costs in the manufacturing process. And then, of course, the digital twins can certainly impact the operation, thinking about sort of every airplane one day or every car coming off the production line with a digital twin that is going to follow it through its life and allow its operator to really make, again, data-driven decisions that are targeted to the individual asset and then on into the post-life and the retirement. So again, I think this is a very exciting concept with wide-ranging potential impact across the life cycle of a complex engineering system. I think the history of digital twins is quite interesting, and I just want to quickly mention the history. The term digital twin was coined by NASA in about a decade ago in a couple of reports that came out around 2010, 2011. But the idea is, of course, much older. This idea of having a virtual model or a virtual set of information that accompanies a physical asset. And many people actually point to the Apollo program as being the first place where this idea of a digital twin was put into practice, because in the Apollo program, NASA would build simulators, virtual simulators of the spacecraft, and keep those virtual simulators on the ground to track while the physical twin, the physical spacecraft, was completing its mission. And this, of course, became particularly relevant and particularly useful during the Apollo 13 crisis. And maybe many of you have seen the movie that kind of glamorizes what happened. That during the Apollo 13 crisis, NASA were able to take data from the real physical spacecraft that was crippled, that had suffered damage due to the issue with its engine, take data from that crippled spacecraft, feed it into the simulator that was on the ground, so that now the simulator was being dynamically updated to reflect the conditions of the crippled spacecraft, and then use that dynamically updated simulator to run the simulations, to run the what-if scenarios, and then inform the decisions that ultimately brought the astronauts back home safely. So that's a really early example, and I think it's also quite interesting to think about just how long ago that was. In 1970, that's 50 years ago, and thinking about the data that they had available and the sensor technology at that time and the computing power that they had at that time and the models. And I think it really reinforces to us that something that we as engineers well know, which is that a model and the data does not have to be perfect to be useful. So today, digital twins, I talked about the roots in aerospace engineering, have expanded far beyond aerospace. So people are talking about digital twins of buildings as a way, for example, to manage energy usage, digital twins of bridges or other kind of civil infrastructure, for example, to guide maintenance and safety. Digital twins in medicine is a very big topic as a way to drive towards precision medicine or patient-specific decision-making. Digital twins of the earth to guide decisions around climate change. And I've even heard people talk about digital twins of entire economies or nations. And so, of course, again, there's a lot we could imagine doing if we had a digital twin of all these complex systems. But of course, there are tremendous challenges. And I think every single one of those systems that I just mentioned, again, it's just not possible to think about modeling the system down to the very last detail. But of course, the Apollo example is a reminder to us that our digital twins can be useful even if our models are imperfect. So with that as kind of introduction, I want to talk just a little bit about some of the gaps and the more of the fundamental research needs that I see for digital twins, and then I'll launch into showing you what we've been working on. So as I said, digital twins are getting a lot of attention, and there's a lot of very exciting early successes out there where people are deploying digital twins for aircraft engines, for bridges, for wind turbine farms. I think it's fair to say that a great deal of the focus in recent years has been on practical deployment, and necessarily so a lot of focus on the data and stringing together the models. But I think if we're going to truly realize the promise of digital twins and to have digital twins with every engineering system that can aid in these critical decisions, then we need to think about the computational science foundations. And I want you to notice that I say computational science, not computer science. So what is computational science, or computational science and engineering? It's an interdisciplinary field that uses mathematical modeling and advanced computing to understand and solve complex problems. And where computational science really differs from computer science is that at its core, computational science really has this notion of a model or a simulation to understand a physical or natural system. And of course, this has very close connections to engineering and the notion of developing models that we have as engineers. So what are these models? These are models that encode our knowledge of the system. Often they come to us in the form of systems of partial differential equations or large systems of ordinary differential equations. And again, computational science as a field has really advanced our ability both to create those mathematical models and then to solve them computationally, so that we can, again, drive better systems, better decision making around our complex systems. So as I go through the talk, I think you're going to see that digital twins need many different elements of computational science and engineering. I already talked about physics-based models, and I really want to emphasize that I think it's essential that a digital twin encompasses a physics-based model. It cannot be built on data alone. And that's because to be useful, our digital twins have to drive decision making that is informed by predictions about the future. Again, thinking about back to that Apollo 13 example, we have to use the digital twins to play the what if scenarios, to make predictions about the future. And if we don't have some notion of a model, a predictive model, then all the data in the world is not going to help us. So the notion of a model, of a physics-based model, is really essential. You're going to see that there's a very large role for inverse theory. So inverse theory mathematically tells us a lot about what we can expect to learn from given data. What can we expect to learn about our system? The role of uncertainty quantification. Again, as engineers, we recognize that in driving critical decisions, that we absolutely have to quantify uncertainties and think about risks. You'll see a large role for surrogate and reduced order modeling to address the computational costs of everything we need to do with and to our digital twin, a role for scientific machine learning, a role for scalable algorithms, and much more. All right, so let's see. I've got, because the screen is, my screen is kind of captured by my screen share. Ratnesh, please don't hesitate to interrupt me if there are questions, because I may not see the chat.
Sure.
Let me now move into telling you about some of the work that we're doing, that we've been doing. And again, as I said, there's a lot of really fantastic work out there in the community with people deploying, sort of creating and deploying digital twins. We are, I just picked up a little echo if somebody's got themselves unmuted. If you could mute, that would be great. Thank you. We're sort of taking a step back and asking, how do we lay foundations? How do we think about defining a digital twin mathematically in a formalized way? And really the goal in doing that is to move from digital twins kind of being this one-off thing where you take your system and you grab all your models and you put them together and then you have a digital twin. We really want to lay a foundation that, again, drives towards this idea of a digital twin with every engineering system, and to do it at scale. So I'm going to step you through the elements of our model, and hopefully you'll see that these elements are very general, but as I go through the rest of the talk, you will see an aircraft and an unmanned aerial vehicle in particular as the particular example. So the first mathematical element that we define is the physical state. So, of course, the state is a very familiar concept to us as engineers, particularly in the controls and dynamics world. But when we think about the state of the vehicle, it's really the state of the physical asset, and you start to think about just what that encompasses. So in the example of an aircraft, the geometry, the structural properties, condition of the engine, the actuators. So very clearly, this state is potentially very, very high dimensional. And what's more, it's multi-scale. It crosses many different scales in space and in time. We're also going to define the digital state. So the digital state are going to be the parameters that define the computational models comprising our digital twin. And in a sense, the digital state is going to be our digital representation of the physical state. But again, I want to emphasize that the physical state is clearly very, very vast. And I think one of the first challenges we have to tackle is how do you define the digital state in a way that makes your digital twin fit for purpose, that it actually models the elements of the state that are relevant to the decisions that you want to make with your digital twin, but also is done in a way that this is going to be computationally tractable, because clearly trying to track states that have perhaps billions of elements may not be computationally tractable. So defining the digital state is going to be one of our mathematical challenges. The third element we have is observational data. Observational data is available information describing the state of the physical asset. And this observational data could come to us in many different shapes and forms. It could be sensors on board our engineering asset. So for example, sensors, structural sensors on board the wing of an aircraft. It could also be inspection data. It could be flight logs. So perhaps many different kinds of observational data. We're going to define control inputs. These are actions or decisions that influence the physical asset. And again, these control inputs might come to us in different forms. They could be control inputs that we apply instantaneously to affect the state of the vehicle. So it could be a control input in the sense of deflecting a control surface on board an aircraft. Or it could be an action or a decision that, for example, influences the data we might collect. For example, we may make a decision that if a vehicle has been damaged, that we want to execute a diagnostic maneuver to collect data that will later on inform us more about what's going on with the system state. Or it could even be that our control inputs are decisions to add sensors to a system so that, again, we might get data in the future. The fifth element are quantities of interest. So these are going to be quantities that we will estimate via our model outputs, or perhaps predict if we're talking about predicting future scenarios. And the quantities of interest obviously depend on, again, the use case. For the structural digital twin that I'll show you, we're interested in things like stress, strain, displacement fields, failure stress, remaining useful life, and so on. And then finally, we'll define the notion of a reward, which is something that quantifies the performance of the asset twin system. And this reward could encompass performance measures as well as costs, environmental impact, whatever it is that we would like to use to quantify performance. Okay, so those are the six elements of the digital twin model that we're going to create. And now I'm going to show you how we take those six elements and mathematically use it to define a digital twin. And I'm going to start off by building what's called a dynamic Bayesian network. And so we're going to start here thinking about the physical space, and we're going to be modeling the physical state. So the physical state here is S, and we're going to be modeling it with a random variable S sub t. So these capital letters, S0, S1, S2 that you see here in the nodes, these are random variables that are representing our mathematical model of the physical state at discrete times here, t equals 0, t equal 1, up to a current time, t equal 2. And in the dynamic Bayesian network, the network relates the states at different time steps through conditional probabilities. So these arrows here represent the conditional probabilities that, again, represent the transition from, in this case, physical state S0 to physical state S1. So here's the physical space. On the second half of the lower half of the slide is the digital space. And again, we're going to introduce the random variable, now capital D sub t, that represents the digital state. And again, the arrows in the Bayesian network represent those conditional probabilities. Here are now the observations, the O sub t's. And of course, the familiar assimilation task is to make observations O sub t of the physical asset and use those observations to infer the digital state. But again, I want you to keep in mind that the state is going to typically be very high dimensional. What's more, this digital state will typically be only partially and indirectly observable through the observational data. So this assimilation task is one that's often very challenging. We're going to add now our control inputs. So the control inputs are denoted with the capital U sub t. And now our dynamic Bayesian network becomes a dynamic decision network because we've now added in the decisions. And you can see here the decisions are going to be driven by the digital state, and in particular by the computational models. Here are the quantities of interest, Q. And again, the quantities of interest are quantities that we can generate using the digital twin models. And again, those quantities of interest will feed into our decisions, into the U's. And then finally, we introduce the rewards, which again formalize the task of determining optimal actions. And the rewards will depend potentially on the observations, on the digital state, on the quantities of interest, and on the actions themselves. So again, here we have a dynamic decision network. Again, I want to emphasize that one of the powers of the digital twin is that it's not just about telling us what's happened to our physical asset. So here we sit at current time TC equal 2, but the power of the digital twin is that we can issue predictions into the future. So here we add a couple more time steps predicting out into the future. And of course, again, we can apply those what if scenarios and use it to plan optimal actions based on the predictions that we have of our models. I want to point out a few things about this mathematical model, again manifested as a dynamic decision network. First, you see the model spans the physical and the digital space, so that's going from top to bottom on the slide. The physical space, where we have the physical state, the observations, and the controls that we've enacted. The digital space.
Karen, there are a couple of hands raised. Can you take questions?
Sure. Maybe let me just finish on this slide, and then we'll jump to some questions.
Sure.
So the physical space with the physical states, the observations, and the controls. In the digital space, we have the digital state, our quantities of interest, the rewards, and then our future predictions. So physical and digital. The model spans the past. So things that have happened in the past as well as future predictions. So that's going left to right. And then the third thing that I want to emphasize is that the uncertainty quantification is absolutely essential to all of this. And I really firmly believe that we have to start thinking about our digital twins, not as deterministic quantities, but rather having models that incorporate uncertainty. And of course, the uncertainty is embedded in all of this because everything here is modeled as a random variable. I kind of like the graphical way to think about the dynamic decision network, but of course, you can also represent it mathematically. And what is it mathematically? It's a giant joint conditional probability distribution, the probability of the digital states, the quantity of interest, the rewards, the future controls conditioned on our observations and on our past actions. And as I go through the talk, you're going to see this joint distribution keep popping up. And what you're going to see is that now all the tasks we have to do to the digital twin and with the digital twin, so the tasks of inference, assimilation, prediction, uncertainty quantification, and decision are all going to be manipulations of this joint distribution, which again is the mathematical representation of our digital twin. So let me pause on that, and let's take a couple of the questions. All right. I don't use Teams all that much. I usually use Zoom, so a little bit unfamiliar. Let me see if I can find the chat. Or Ratnesh, do you want to?
Yeah, sure. Yeah. So we have a hand raised by Mahendra Singh Rotela. Perhaps you can go ahead. I think you're not very audible. Maybe you can try to speak up.
We can hear some birds chirping, but no question.
Yeah, I don't see him in the meeting, so maybe we can move on to the next question by Pradipta Biswas.
Hi, good morning, Karen. So I have rather two minor questions. So first question is this diagram. It's kind of resemblance this utility diagram, in which case we add this utility node with the dynamic Bayesian network. So in your particular diagram, is the variable u or the r denotes utility?
So the variable u are the control actions, and the r are the rewards. So I think I'm not so familiar with utility diagrams, but I think the utility tends to be the objective function, right? The way you quantify performance, and so that would be analogous to the reward here, the r.
I see. Yeah, we calculate the mathematical expectation. So, and the other question is you make a first order assumption. That means the state st is only dependent on st minus 1. So is it just for computational reason?
Absolutely. Yes. So I'm going to mention that assumption on the next slide that we have the, we're building this as with Markovian dynamics, so that exactly what you said, the state at S1 is only dependent on S0. And I mean, partly that's for computational reasons, but that's also the way that we've chosen to model it, with the notion that you should define the state in a way that actually is true. And of course, I mean, maybe for those of you who have controls and dynamics background, you'll see that I'm very much using the language of controls and the notation of controls here. And so honestly, in many ways, I think this is very much like an optimal control problem, with maybe the difference that when we say state, we're not just meaning position and velocity of a vehicle while it's flying. We're thinking about its geometry and its material properties and the way it's manufactured. And so the state is much more complex. But yes, you're absolutely right. We have that Markovian assumption embedded in this representation.
All right. Thank you.
So am I audible, Ratnesh, sir, now?
Yes, we can hear you now.
Yeah. So hello, Professor Karen. I had a question which I think you have already answered to Professor Biswas. So the question is, this framework looks much more like a Markov decision process in which an agent interacts with its environment. And the question was like first order dependence and the higher order dependence.
Yes.
It's like how this Bayesian network, or you said a dynamic Bayesian network, is different from a dynamic programming or overall dynamic programming platform where there is an entire Markov decision process.
No, you're absolutely right. And just to sort of emphasize, what you're going to see is that, there's nothing new about this network. This is sort of, as you point out, very much aligned with the kinds of networks that you see in, it is just a dynamic decision network, but in dynamic programming formulations. And in fact, you'll see that we'll be using dynamic programming to solve the optimal control problem when we get to deploying the digital twin for decision making. And really the contribution here is to take that formalism and to put the digital twin in that setting, to really say, what is a digital twin? Well, let's think about it. Let's identify the notion of a state and controls and observation, and then let's formalize it and put it into this language of Bayesian networks probabilistic graphical models. And then the power of doing that is now we can reach for all the methods that exist for solving the optimal control problem, for solving the data assimilation problem, for the optimal experimental design. But of course, as powerful as those methods are, I think dealing with the complexity of the digital twin, the dimension of the state, and that multi-scale nature it's still a challenge. And there are many of the methods that are used to solve these kinds of problems just don't scale to the kind of complexity of the problems we have here, especially since embedded in our digital state, we're going to have things like, the Navier-Stokes equations to predict the flow, or the equations of linear elasticity, the PDEs that will predict the structure.
Thank you, Professor.
All right, are there any more questions?
Yes.
We'll going?
Yes, Professor. Yeah, Professor Karen. My name is Vinay Ramnath. I with Siemens Technology. I think if I understand your dynamic network, I guess at every time step, the models are getting calibrated with respect to the observations, right? I think that's the context of.
That's right. And in fact, I'm going to step through some examples now. And what I'm going to show you is, so depending on where you are in the life cycle, this network is going to manifest kind of in different ways. And so what I'm going to do next is show you, for example, when you're calibrating the model, you have a certain set of decisions and observations, and you manipulate in certain ways. Whereas when you have a calibrated digital twin, and let's say you go out and you're in operation and you're driving decision making, things are going to look a little bit different. So I think I'll get directly to your question when I walk through the example and show you how we construct the digital twin and then how we use it.
Okay, thank you. Thank you.
All right, I think we have one more question.
We have Nurtaj, you can go ahead. I think you have to unmute. No, I don't see a response. Maybe we can move on and have these questions towards the end, probably, right?
Yeah. Okay. Let me keep going, and
sure.
And then we certainly can take more questions as we go. Okay. All right. So now what we have is we've defined the elements of the mathematical model, and I've shown you the topology of the dynamic decision network. And actually, I should also say there are different ways you could think about putting this network together, and that goes to some of the questions. This is one particular manifestation of it. We do have a few assumptions, and in fact, I forget who asked, but it was a very good question, that we are assuming Markovian dynamics for both the physical state and the digital state. We have it set up so that we're observing the physical state only indirectly. So in general, we're assuming that inverse problem, again, only gives us indirect observations, which may or may not be true in systems. But again, as engineers, we know that it's often indirect observations only that we can get of our systems. And then again, just a choice of the topology. You see that the control inputs, the UTs, are informed by the digital twin analysis. By running the digital twin models, we're not driving the control inputs directly from the observations. But again, the flexibility is there if you wanted to model things in a different way. Again, what mathematically, and I'm not going to dive into the probability distributions too much at all in the talk, but again, just to point out that there's the network, and mathematically it's this joint distribution that really is the mathematical model. And in particular, the conditional independence structure defined by the graph admits a factorization. And I do want to just talk about these 5 factors, because I think that, again, that'll start to answer some of the questions. You'll see that these 5 factors are going to embody the different tasks that we want to do to our digital twin, the updating and the calibration, and the different tasks we want to do with our digital twin to drive decision making. So let's just step through those 5 factors. The first one there is the phi dynamics. That's the digital state transition, the transition from state dt minus 1 to dt given the action ut minus 1. The phi q of I, that's the quantity of interest. So the probability of the quantity of interest conditioned on the digital state. So that's basically the forward models that says, give me the estimate of the health of your aircraft wing, and I'll issue you the predictions of the quantities of interest. I'll issue you predictions of stress and strain or failure indices. So again, that quantity of interest is where our predictive, often PDE, partial differential equation models are sitting. The phi eval here, this is the reward function. So this encodes the dependency of the reward function on the digital state, the quantity of interest, the controls, and the observations. And again, that may be a sophisticated model, maybe sort of a sophisticated, let's say, structural damage model, or it may be a simpler definition of the reward. And again, to the question on utilities, this is the term where if you had utilities and sort of decision maker preferences, they would be embedded. We have this phi assimilation factor. So this is this is the likelihood, the probability of the observation given the digital state. And then we have the control term, which relates the controls to the digital state and the quantities of interest. And what you notice is that this control term is active only over the future. So notice the product here going from the current time to the prediction time. So this is about future controls. The assimilation term here with the likelihood is over the past. So this is the assimilation of things that we've observed from the beginning time to the current time. And then the other three, the dynamics, the quantity of interest, and the reward function are over the full horizon from the past and into the future, into our prediction horizon. And again, there's a lot of sort of probabilistic manipulations that will go on, but I just want to emphasize that this graph leads to this factorization, and we work with this factorization for a few reasons. One is this now reveals the tasks of updating, predicting, and decisions. And as I step through and I show you how we do an update of the digital twin, or how we do a control decision with the digital twin, you're going to see different terms in this factorization kind of lighting up and becoming active. And second, factorizing in this way actually helps to make the whole thing tractable, because now we can endow the digital twin with computational models and again work with the pieces that are relevant. All right, so for the rest of the talk, I'm going to use a concrete example just to try to make all this a little bit more concrete. And that example is creating and evolving a structural digital twin for an unmanned aerial vehicle. And what I'm going to do is I'm going to step you through starting with a baseline model, calibrating a digital twin to a particular physical asset. So we're going to calibrate the geometry, calibrate the material properties, and calibrate mass and damping factors. Then we'll have a calibrated digital twin, and then I'm going to show you how we might use that calibrated digital twin to drive dynamic decision making. And in particular, we're going to consider dynamic estimation of structural health. So when the UAV is flying and undergoes some kind of a damage event, we're going to dynamically update the digital twin and use it to drive mission replanning. And as I step through these different elements, I'll give you concrete definitions for all the elements of our dynamic decision network. So I'll in each case call out what are the control decisions, what are the observations, what are the quantities of interest, what are the rewards, and so on. Before I go into the computational piece, I just want to show you the hardware that we have for this particular project. So we have a customized 12-foot Telemaster aircraft. This vehicle was designed and manufactured together with Aurora Flight Sciences and my group at MIT. We did this when I was still at MIT. You can see here a picture of the vehicle. This is a picture of the vehicle at its first flight test in Massachusetts about 1.5 years ago. It's been designed with removable wings, so the wings pop in and out of the fuselage so that we can have different wings in different states of structural health for testing. We also have a lab benchtop setup, so we have this fuselage mount and we've been doing, we obviously can do a lot more tests and collect a lot more data if we can do ground testing rather than having to rely on what we can get out of flight tests. But the vehicle has flown a couple of times. One of the challenges of course, the pandemic and campus being closed has been access to the labs. So in fact, the vehicle is right now here in my house where I'm sitting this morning. It's actually downstairs in my garage, and you can see I had to recruit. This is my middle school son who had to get recruited to help take data. He's not so happily collecting strain data from a scope in that picture, but it's been fun. It's been fun for the family to have a test bed in the house. A little bit about the computational models. Again, we're going to focus on building a structural digital twin. So, and again, the physics-based model is absolutely a critical underpinning because we want our digital twins to be predictive. We want them to be able to issue predictions and supportive decisions. Our structural model has at its heart a linear elasticity model. So here are the equations of linear elasticity. You can see here a schematic of the finite element model. And just to kind of emphasize that, again, we're trying to build a model that represents the physical vehicle. So here's a picture of the inside of the physical wing. And you can see that our finite element model reflects that with the different material types, different element types, and so on. The finite element model takes about a minute per structural analysis, which, is fine if you're doing a couple of analyses. But as you can imagine, as we get into the probabilistic updating and the also control decisions in real time, we certainly can't be waiting 1 minute for a finite element model to run. So we also create reduced order models. We're doing reduced order models using the static condensation reduced basis element, the SCRIBE method from Tony Padere's group at MIT. This is an approach that breaks the system, in this case the wing, into multiple components and builds reduced models for each component separately and then integrates them for a system analysis. And so this is an approach that really lets us deal with many parameters and also is very amenable to the kind of dynamic updating that we're going to do when we put the digital twin into operation. You can also see that the reduced models run much, much faster than the finite element model. And we've been working on both the finite element model and the reduced order modeling together with Axelis. Okay, so we have the physical twin, we have the physical UAV, and we have the computational models, in this case, finite element and reduced order models. So now we're ready to create the digital twin. And the very first step is that we have to think about what the digital state is. And as I've already mentioned, I think this is a very challenging but very interesting question, is how do you define the digital state in such a way that the digital twin is fit for purpose, but also computationally tractable. So here's the digital state that we're going to work with, and the example I'll show you. And I want to just point out that this digital state has 3 different flavors of variables. It has variables that represent asset-to-asset variability. It has variables that represent unmodeled hardware, and it has variables that represent unmodeled physics. So on the asset-to-asset variability, again, we have to remember one of the ideas of the digital twin is to tag it to individual assets so that we can track their differences. So in particular, the vector of geometric parameters and this Young's modulus scale factor are going to represent differences in geometry and material properties that might, for example, be due to manufacturing processes. We're also going to have a vector of structural health parameters that are going to reflect different operational histories. As you manufacture thousands of these UAVs and they all go off into operation, clearly they're going to degrade and age in different ways depending on how they're maintained and how they are flown. So the geometry, the material properties, and the structural health are all parameters that represent that asset-to-asset variability. The vector of added point masses here, this represents unmodeled hardware. And if I flip back to the picture of the wing, we recognize, and of course we know that, it's a lot more than just a clean wing. There's all kinds of things on board the wing, such as these servo motors that drive the ailerons. And so now we have a choice when we create our finite element model, which is, do we try to resolve every last detail of the vehicle which would give us a very high fidelity model, but is going to be perhaps computationally intractable? Or do we create a simpler model and then introduce parameters that capture some of those missing, in this case, hardware? And that's what we've chosen to do with these added point masses. So that's going to be capturing all the hardware that we didn't put into the finite element model. And the Rayleigh damping coefficients here are similar, but now rather than unmodeled hardware, this is unmodeled physics. Again, we choose to go with a simpler physical model, but then we're going to introduce Rayleigh damping coefficients that are used widespread in engineering to model internal structural damping. And again, I want to emphasize that because we're treating things probabilistically, our models do not have to be perfect. I think it's a real mistake to think that a digital twin has to model everything perfectly down to the last detail. It's okay to make modeling assumptions, to introduce these parameters that embody those assumptions, and then again, we're going to treat things probabilistically. So because we're treating things probabilistically and we're going to do the updating in a Bayesian way, we'll need prior information. You see here the prior information that we have on, for example, geometry parameters, this Young's modulus scale factor, on the masses, and on the Rayleigh damping coefficients. Okay, so let me step you through, and Ratnesh, should I talk until, or tell me at what time you want me to stop talking?
I think we are going fine. So
we're going fine. Okay.
Yeah.
All right. So I'm going to step you through some of these steps that we saw in the overview, and the first one is going to be to calibrate the geometry. So here, the decision that we take is an action to go and measure the geometry of the physical asset. The observations that we make are the observed geometry. So in this simple example, we're going to measure the wingspan and then the chord at the root and the tip of the wing. Quantities of interest in this case are just going to be the geometry. The reward maybe doesn't play such a big role, but for example, we could define the reward here as the change from the prior to the posterior, which might be, for example, a measure of how well the wing has been manufactured. And this could, you imagine, could be a measure of performance that you would feed back into a manufacturing process. So here's the prior information. The prior come from the engineering specs that we have, in this case, from Aurora Flight Sciences. Observation, go out into the field, measure the UAV, and then we can do the Bayesian update, taking the observations, updating the prior to the posterior. In this case, because we can measure the geometry very accurately, we're not going to track uncertainty in the posteriors, and we're going to, going forward, just represent the geometry deterministically in what I show you. The second step is to calibrate the material properties. So for this, our decision is to conduct a load displacement test where we apply a tip load, a known tip load, to the wing and then measure the corresponding displacements. This is a static test. The observations are going to be pairs of that tip load and the displacement. The quantity of interest we define here as an aggregate stiffness, that is the ratio of that tip load to the measured displacement. And the reward here is going to be the reduction in variance from the prior to the posterior. So this is a reduction, this is a measure of how much uncertainty do we reduce by actually doing an experiment on a given wing and trying to understand exactly what its material properties might be, or at least reducing the uncertainties and what the material properties might be. So here on this plot, you see some of our experimental data. So here's the plot of the tip force versus the tip displacement, and we're seeing here 8 different measurements along with their 95% credible intervals. You see here on the right the probability distributions of that Young's modulus scale factor, the prior in light blue, the likelihood in red corresponding to this particular observation, and the other likelihoods shown here. And then again with the Bayesian update, we move from the prior to the posterior. And you can see we update both our mean estimate of the Young's modulus scale factor as well as its variance. And the prior in this case is Gaussian. I know the posterior looks kind of Gaussian, but it's not because the likelihood is non-Gaussian. So we have a sampling together with kernel density estimation and then the Bayesian update via a particle filter. And that's due to the nonlinearity in in this term here. And again, that sort of allows us to update this quantity of interest, which is this effective stiffness from the prior to the posterior. So now we've taken 2 steps and we're calibrating our digital twin. We've calibrated the geometries and we've now calibrated the material properties. We now have this posterior estimate of the material properties, and we're going to take forward this distribution so that, for example, when we use the digital twin to drive decision-making in operation, we'll also be accounting for our uncertainty in the material properties of the wing. So we're going to carry this full distribution forward. All right, third step is calibrate the mass and the damping. So these are the added masses and the Rayleigh damping coefficients. Here we do an initial condition test where we displace the tip and let it go, and it oscillates and then it settles back to steady state. So we're tracking dynamic strain measurements. We have some flexible stickers on the wing that allow us to measure dynamic strain, and we do a bit of post-processing of those results to extract out frequency and damping information. Quantities of interest, again, are the frequency and damping. And the reward here is measuring the fit of the model to the experimental data. And I should just briefly mention here that I taught signals and systems and controls for many years at MIT. I don't know if there are any students on the line, but it's always fun to see a system that exhibits sort of the beautiful second order system response. And you can see that here, seeing the signal from the dynamic strain measurements versus time, that you see again that nice decaying sinusoidal behavior. So it's a relatively simple model that we can fit to that data that again lets us calibrate these added masses and the Rayleigh damping coefficients. And again, here you can see the update from prior to posterior, and you can see these distributions that we'll be taking forward. So now we have a calibrated digital twin. It reflects the geometry, the material properties, and the structural properties of the physical UAV, of the particular one that we've done the calibration on, and our estimates of uncertainty. We can now take that digital twin and think about using it in operation for dynamic decision making. And the particular example I'm going to show you is one where we think about the aircraft flying and undergoing some kind of an in-flight structural health degradation. So imagine, this is a UAV that's flying and maybe gets hit by something, and it's now got damage on one of its wings. We have wing-mounted sensors that provide noisy strain data. So those are going to be the observations, the strain data. The decision now is going to relate to mission planning. So in this particular example, the vehicle has to fly through these buildings, and it has a choice of either flying the conservative path shown in blue, which takes longer and will burn more fuel, but is going to pull a lower load because the turns are not as sharp, and so it's not going to worsen the damage and it's not going to load the wing as highly. Or it can fly the more aggressive path shown in orange, which is faster, but again pulls more loads and so can worsen the damage. So that's the control, the decision. The UT here is 2G or 3G maneuver. Again, the observations of the strain, the quantities of interest are going to be the predicted strains from the model. And now the reward function plays a big role, because the reward function is what will drive this optimal choice of the maneuver. And the reward function has components that relate to the health of the vehicle, so not worsening the health too much, the control of the vehicle, so choosing a control that has minimum energy, in other words, driving towards the faster path, and then also potentially a term that relates to the error. So at the same time as you're making decisions, you're also able to collect data and drive matches with your predictions and matches between your predictions and your experimental data. For this particular example, what I'm going to show you on the coming slides, these are simulated data. So this is not actual flight test data. The previous data was real data from the UAV. This is going to be just simulated data, and we use ROS, the robot operating system, as an implementation for this. All right. So here's the digital state. It hasn't changed, but I've just put it up here to remind you and to point out that we've calibrated the first 5 elements of the digital state. And now in the dynamic updating, we're going to be updating the structural health parameters Z. So the other parameters are fixed, but they're not fixed deterministically. They're fixed with their posterior distributions. So again, we will be carrying forward the uncertainty in the material properties and in those damping coefficients as we use the digital twin to drive decision making. Again, this probability distribution and its factorization plays a key role. In this case, we have a couple of factors that I want to highlight. The first one is the dynamics model for the damage. So for the structural health parameters, as I mentioned earlier, you could have a sophisticated physics-based model sitting in here. For the example I'll show you, we have a fairly simple damage progression model, which is to say that the structural health has 5% probability to worsen by 20% under the 2G maneuver and a 10% probability to worsen by 20% under the 3G maneuver. And you can imagine that's a progression model that could be based on collecting data across your asset fleet, or the kind of empirical models that are used. Or again, if you had the time to do the simulations, you could have a more sophisticated physics-based damage model. And then, of course, the likelihood there to drive the assimilation. So the next element we need a control policy, pi, that maps our digital state and our prediction of the quantities of interest into an optimal action. We're going to define that control policy by maximizing an expected accumulated reward over the prediction horizon. So here we are taking the expected reward over the future, over the prediction horizon, and gamma here is a discount factor. And we would look for the policy, the optimal policy that maximizes this reward. So for those of you familiar with dynamic programming, this is a fairly standard way to approach the optimal control and planning problem, dynamic programming or reinforcement learning. Now, finding this optimal policy is in general intractable, so we have to make a few simplifying assumptions. For example, we approximate this planning problem as a fully observable Markov decision process. We use an infinite planning horizon. These are kind of the standard tools of the trade in dynamic programming. And basically where that gets us is that we look for a suboptimal policy, this pi tilde, that is a function of D star and Q star. And D star and Q star are our maximum a posteriori estimates of the digital state and the quantity of interest. And this can be solved for using a standard value iteration algorithm. So again, I don't have time to go into the details, but again, we're sort of using, fairly standard tools for solving these kinds of dynamic programming problems. Here's the reward function for the particular example I'll show you. It balances the UAV wanting to complete the mission quickly with the aggressive maneuver, but not being too aggressive so that the health starts to degrade too quickly. And so here's an example of, again, simulations from Ross that show how all that comes together. So what we're looking at the top here are the digital states. And again, we're tracking the structural health parameters. In this case, 2 structural health parameters, Z1 and Z2, that correspond to these 2 shaded panels on board the aircraft. And you can see that we have not just our estimates of the structural health, but also the uncertainties. And you can see that we have a lot more confidence in what's going on inboard to the wing than we do going outboard. And that's got to do with the dynamics and the available measurements that we have. You see here in the middle, both our observed in the dots, those are the observations, the observed strain, and then the estimated strains, estimated using our reduced order models of the wings. And again, so we're looking here at 3 different sensors. And again, you see both the estimates and our uncertainty in the estimates. And of course, you see the estimates growing as we move from estimation of the past into prediction of the future. Here, the third one here, you see the control inputs. You can see we start off flying aggressively. And then at this point here, at about t equals 35, the digital twin says, hey, the structural health is starting to get is worsening too quickly, it's time to switch to now flying the more conservative maneuver. So these are decisions informed by the digital twin. You can see there in the line, that's the actual optimal decision. Gives you a sense of how all this comes together. Now, I just want to close with a few thoughts. Again, really the key contribution of this work is to propose a probabilistic graphical model as a mathematical foundation for a digital twin. It just gives us a way to think very systematically about defining a digital twin. And when we do that, we have now a dynamic decision network, and we can layer on top of that all of our favorite Bayesian methods for doing the updating, the calibration and the updating, and for driving optimal decision making. The second point that I've made a couple times, a digital twin cannot be deterministic, not if it's going to be something that supports critical decisions where societal risk and people's lives are at stake. Uncertainty quantification has to be a part of the way you even think about your digital twins. Third is scalability is a real challenge. You've seen just a little bit of the methods that we use, and you see things like Bayesian updates, particle filters, dynamic programming. And I'm sure you all well know that scalability to high dimensional problems is a real challenge. But of course, there's a lot of work out there and structure exploiting methods, surrogate models, and I think even more exciting work to be done there. And of course, this is just a start. There's many other fundamental questions that remain. I'm particularly interested in the optimal experimental design question. As I said right at the beginning of the talk, one of the, I think, very interesting things about digital twins is that they may enable us as engineers to think very intentionally about architecting the information flow and the sensors in our products, and really thinking about how one trades, for example, the weight and the power requirements of putting extra sensors on board an aircraft, trade that with the value that might come later by having that ability to sense, and how that might mean you could drive optimal operation. So the digital twin I see as a new tool to assess those kind of trade-offs. The second one here, learning across an asset fleet, I think that's also very interesting. You know, digital twin is tagged to a particular, let's say, UAV, but now imagine that you're Amazon in the future and you've got fleets of thousands of these UAVs. How do you share data across that asset fleet and use it to drive, especially some of this probabilistic modeling that, again, will improve digital twins for all of your vehicles and help you maybe identify issues and get out in front of them before they happen. All right, with the very last slide here, again, I just want to come back to this notion of computational science and engineering in a field as a field, and think about the role it plays. That for 6 decades, this is a field that really has been advancing scientific discovery and engineering innovation through powerful forward simulations, through CFD, through finite elements, through PDE solvers, through the optimization and inverse theory that shows up in parameter estimation and design and in control. More recently in uncertainty quantification and all the methods that have really equipped computational models with quantification of uncertainty. And then today we hear so much about machine learning and data science and AI. And I think these are very powerful tools that can play a role in everything that we do, especially in something like a digital twin. But again, I think it's important that we don't shine so much light on this last one that it kind of blinds the rest of them, because I really firmly believe it's all of these things, the physics-based simulations, the inverse theory, the uncertainty quantification, and the scientific machine learning together that are the only hope of truly addressing the grand challenge problems that we face as engineers. So with that, let me close. If you would like to learn more about what I've talked about today, especially, you can go to my website here, kiwi.odin.utexas.edu, and there is a paper that describes Michael's work. And other than that, let me stop, and I'll be happy to take more questions.
Thank you, Professor Wilcox. I think we have two hand raises. Perhaps Pradipta can go first.
Thank you, Professor Karan. Am I audible?
Yes, we can hear you.
Oh, thanks, Professor Karan. That's very interesting. Just I have another small question. So it's about the penultimate slides. So when, say, we cannot observe the states directly, then we go for the reinforcement learning. But here in this case, since we are defining the states ourselves, so can't we use the policy equation algorithm or Bellman equation to find the optimal policy? And I'm just and why we should settle for a suboptimal policy?
So the reason we settle for a suboptimal policy is just the tractability of the problem, because, I mean, yes, you can solve it optimally if you can afford to do the full iteration, right? But what do we have here? So we're observing the strain, and we have a number of observations from the strain sensors. We're then using those strain observations to estimate the structural health parameters, the digital that's part of the digital state. So those structural health parameters, are parameters in a finite element model, which, and again, we're using a reduced order model, but even with the reduced model, you then got to run the simulations, and you've got to do all this while tracking the uncertainty. And so the suboptimality is really just a way to make it tractable. I think for any sort of reasonable engineering problem, the complexity and the costs of the models that you're going to have to run are going to force you to reach for those kinds of approximations. But you raise a very good question, which is, how do you do better? And again, this in itself is an optimization problem, because the question is, how much time do you have to make the decision? The UAV is flying, and you got to tell it right now which path to take, and having the optimal decision too late is definitely not as good as having a suboptimal decision in time. And so that's sort of, again, one of the trade-offs that we've made. We've been thinking about the real-time implementation on board the vehicle.
Absolutely, ma'am. Thank you. And I will get in touch offline. Thanks. Very interesting talk. Thanks.
Thank you.
Nurtaj?
Thanks, ma'am, for giving this talk. I'm Nurtaj Hossain. I'm a PhD student here. So here I have two questions here. So before employing this reduced order model online, do you construct a robust reduced order model first? For giving range of parameters.
Say it again. Before implementing the reduced order model online, do we?
Before employing this reduced order model for digital twin purpose, did you construct a robust reduced order model for giving parameter range of interest?
Yeah, so that's a great question. So I didn't talk much about the reduced order models. That's a whole nother talk. And actually, Michael, we have a paper with Michael on that. So I mentioned very briefly this component-based reduced order modeling approach. And basically what that enables us to do is take the wing and divide it. And we and what I showed you here, we divide it into 15 components. So you imagine taking your wing and breaking it up into little pieces. And now each one of those pieces, we have damage parameters associated with it. And we can do this because, damage is largely a relatively local effect. And the scribe methodology lets us take those component-wise reduced models and then assemble them using kind of the theory of static condensation, if you're familiar with that, and the kind of thing that people do with substructuring in finite element models. Yeah. So let us take those components and assemble them to predict the response of the entire wing. And one of the reasons that we go that approach, there's really two. So one, you asked about the robustness of the reduced models. Because you've got to build at the component level, you can really, sample over those damage parameters, because you have now just to deal with the local damage parameters. Whereas if you're doing it at the full vehicle level, you could imagine just how many parameters you have, and doing the training of the reduced models would become a real challenge. And as you suggest, the robustness could be a question. So that's the first reason to do it. And then the second reason to do it is the component-based approach is really amenable to the dynamic updating. And again, I didn't talk about this piece, but when we do the dynamic updating, what we're basically doing is taking, I sometimes think of these components as being like blocks of Lego, and the blocks of Lego that are pieced together to give a full wing. And then when you have something that's damaged, it's like you pull out that Lego piece and you put in one of a different color. So we've got all these reduced order models built ahead of time for different damage states, and we can really quickly pull one out and put another one in. And that's how we can do the updating of the physics model very, very rapidly. So there's kind of like a lot that sits under there. And then maybe just the last part to your question, because we're working with linear elasticity, with a few things added to account for some of the structural degradation, but linear elasticity is one of the PDEs for which the reduced basis method comes equipped with error estimates. So we can actually quite rigorously go after your question of robustness in the creation of the reduced models. And we can really ensure that the reduced models are going to issue accurate predictions over the range of conditions that we expect to see.
So I have one more question. Do you update the damage model online? For example, I have a plasticity model, and if I found that that plasticity model doesn't work, do you update that plasticity model online as well?
Yeah, so we don't have a plasticity model. Our damage model that we have right now is introducing changes in the material properties into our linear elasticity model. So and again, this is a modeling choice, but basically we make the argument that if you're flying on the vehicle in real time, you don't have to capture all the details of the damage. What you need to know is how, what's the capability in the vehicle. So I'm damaged, I've got some damage on my panel of my wing. What I actually care about is how fast can I fly? How tight of a corner can I turn? What loads can I sustain? So we have a much simpler damage model that we're updating as the vehicle is flying, with the idea that once the vehicle has landed, that's when you would invoke your more sophisticated damage models, but then you would also bring in its, inspections and visual inspections, and then that would be kind of a whole nother layer of higher fidelity assessment. So in what I showed you today, we have a much simpler damage. In fact, we probably really shouldn't call it damage model, structural health degradation model.
Thanks, ma'am. I'm done.
Dr. Harinarayana. I think you can.
Dakota, we are not able to hear you. Dr. Kota, we are not able to hear you.
Yeah. Can I talk now?
Yeah, we can hear you now.
I would like to first thank Professor Karan for a wonderful talk she has given. I have two observations. One is the digital twin. I thought we could use it very effectively to plan the manufacture, especially with a jigless manufacture. Is that a right direction to think? That is number one. Number two, offline I can do a lot more simulations about deployment, health with the damages and all, and use that information for a realistic deployment of the vehicle. These are the 2 points I want to make. I would like to have the comments of Professor Karan.
Yes, thank you for the comments. And so for the first point, absolutely, the using the digital twin for manufacture, I think, is a fantastic application. It's not something that I work on because I'm not really in that space, but I think it's a really fantastic application. And I think, again, to emphasize the tracking of uncertainty, because so much of manufacturing is about reducing variability. And so if you have a way to equip the digital twin with its estimates of uncertainty, I think it could become a very powerful decision-making tool for manufacturing processes, for quality assurance, for sort of continual feedback. So I agree entirely. On your observation with the offline simulations, yes, I agree entirely with that too. And sort of the reduced order models are one manifestation of that. That reduced order models, we have to do a lot of expensive simulations on the ground, offline, to build the reduced models. And then the reduced models are our now simplified physical model that we can afford to run online. So that's the way that we sort of take advantage of that. But of course, there are others and other forms of surrogate modeling. But absolutely thinking about how you layer your digital twin. I talked about multiple scales. There's sort of this idea that you can afford to do expensive simulations on the ground. And so I could imagine a future where, the UAVs are flying around and they're collecting data and they're doing updates while they're flying with simple models to guide their flight on any given day. And then they come and they land and they basically plug into the USB port, download everything, and then the high fidelity models start running and you do a high fidelity update. And so thinking about how you do all those things on different timescales with different models, again, I think is very interesting. And I'm sure some of that is done already. For example, in the GE digital twins of the engines, I'm sure they do things like that already. But thinking about how we formalize it and how we create methods that let us do it at scale is probably where the challenge is.
Thank you.
Professor Simba.
Thank you very much, Professor Karen Wilcox, for a wonderful introduction and a perspective of a digital twin, which I never heard of. So I learned something with your lecture. I had one question, that whether digital twin has reached a level of maturity that it would be made mandatory for all the UAVs which are coming in a big way into several commercial spaces, and whether it is possible to use your digital twin approach to actually figure out when a particular device could be planned for retirement. These are two questions which I hope you throw some light on. Thank you very much for a wonderful talk.
Thank you. Well, mandatory is a very strong word. But you asked, have they reached a level of maturity? And maybe our guest from Siemens will disagree with my answer, but I would say no, not yet. I think they're at the point where there's there's been a lot of successes and there's enough maturity out there to really show what is possible and to make it worthwhile to invest in. But are we at the point where we can build an engineering system and create its digital twin and have confidence that the digital twin is computationally tractable and is truly predictive and has quantified uncertainties and can be kind of sent out of the factory door together with the physical twin to a company for its life? I think the answer is right now no. I think we still have a little ways to go. And I sometimes draw an analogy with the development of the finite element method. So, again, if we think about the history of the finite element method, was really back in the 50s where the very first finite element analyses were done. And of course, it was in structural engineering in aerospace and civil. And those very first developments of the finite element method were done by experts, right? I mean, it was sort of, you had to build your own, and it was only a very small set of experts that used it. And then you think now in the past 60 years, what's happened? Well, the mathematical methods have really matured so that now, somebody asked earlier about robustness, that you don't need to be an expert to tune everything, right? You can push a button and have a piece of software generate a grid for you and do finite element solves, and it just works because the mathematical methods are robust. Second is we have more computing power so that we can actually create finite element models that are of sufficient resolution to be predictive. And third is we have, a tremendous industry of software and products that support engineers. And so that's taken the finite element method from being something that was in the hands of experts and just a few to being something that's on the computer of every engineer, literally every engineer. And I think the same thing has to happen with digital twins, but I think we're still very much in the early phases.
Thanks so much. Have a great day.
Thank you.
Mahendra?
Am I audible, sir?
Yes.
Yeah.
So that was a very wonderful presentation, and I'm a PhD scholar in aerospace department. I work on hybrid learning models. So my question is, what was the role of machine learning in means like you have presented a talk, and I didn't see any role of machine learning along with physics-based model in the presentation. But I read one of your paper which talks about interpretable machine learning. So I was a bit confused, means like how machine learning will enter into the picture. Whether we have to train our model offline, then do all the predictions online, or as per your talk, it looks like everything was online, updation and all things.
Yes. So we've done this dynamic updating in a couple different ways. And in what I showed you today, we're using dynamic programming, which, by the way, now is called reinforcement learning. So I guess in that sense, it is machine learning. It's reinforcement learning. I still refer to it as dynamic programming. But in what I showed you today, we're using that formulation with the looking for the policies. In the paper that you're referring to, we've also treated the online updating using optimal classification trees. And you're exactly right. What we do there is we do a lot of the simulations ahead of time to train these optimal classification trees. And then we treat the problem of updating the digital twin as one of taking the data, classifying the state that you are in, either deterministically or probabilistically, and then doing an update. And, I think both are sort of powerful ways to think about doing dynamic updating of digital twins. The reason I presented the dynamic programming work here is because it flows a little bit more naturally from the probabilistic graphical model formulation that I presented in the beginning. But certainly you could think about using classification or, other forms of machine learning, absolutely, especially in that online updating phase.
Thanks a lot.
Ramu?
Yeah. Hi, Karan. Thanks for the great talk. The sort of perspective that you have given with this talk is digital twin in the operation state of a particular structure that we are looking at. But can this be used at the design stage? You did show in your summary slide that we can use this for designing experiments. Can you shed a little bit of light, like how can we use this at the design stage? How can we use digital twin at the design stage?
Yeah, that's a great question, and I think this is a very interesting question that actually could go in many different directions. So the first one, that I've already mentioned a couple times is that when we are designing the vehicle, we should also think about designing the digital twin. So we should think about designing a vehicle that is going to have a digital twin, and you could imagine that the vehicle you would design would be different if you knew that it was going to have this digital twin with it, because, for example, this starts to get a little bit tricky because as aerospace engineers, we have certification and, obviously safety is paramount. And so it gets hard to talk about changing that. But let's imagine that we could have all constraints lifted and just do a thought experiment. You could imagine that, for example, instead of designing into the structure those, all the redundancy and the reliability that we have, which, by the way, what do? We do very refined calculations and then we throw in safety factors. And I think in civil engineering, it's much the same, right? We throw massive safety factors. Instead of doing that with the physical vehicle by beefing up the structure, could we start to think about bringing in that safety and reliability through the digital twin? Now, of course, to do that, we would have to have absolute confidence in our digital twin, just like we have absolute confidence in our physical structures. But I think that's an example of how the digital twin could potentially change the way we think about design. Although again, we have to be able to ensure safety. So that's one. Another one is thinking about the sort of the feedback. You know, again, if you're designing a 777, then the lifetime of the vehicle is so long, and relatively speaking, you manufacture so few that you're not going to be making changes to the design once you've manufactured the first few. But if you imagine a future where we have autonomous vehicles doing cargo delivery, or maybe even one day doing urban air taxis, we're going to be in a situation where we'll be manufacturing thousands and thousands and thousands of these vehicles. So thinking about how the digital twin can play a role in tracking both in the manufacturing and in the operation process, and taking that data and feeding it back to inform the design of next generations of vehicles, I think is another very, very interesting area to think about. And again, as you know, that's going to make sense in situations where you're generating a lot of products and they're being turned out very, very quickly. So yes, I absolutely think there's a role in the design phase. I think there's less being done. It seems that the digital twins that have been deployed have been a little bit more focused on operational support and manufacturing a little bit.
Okay, thanks for the insights.
Karen, this is Suresh. Yeah, thanks for giving a great talk and describing the architecture for digital twin. You also at the beginning that applications are many, especially in medicine or digital twin for human health. If you take, then the events are not going to change as quickly as it happens for a aircraft or an engine, right? So in that case, the framework remains the same, and other thing is having the predictive capability in a digital twin. When things change slowly, like human health, for example, can you, or in the case of engines as well, can you prevent at some point when the technology becomes mature, an accident or some damage? That is, you take precautionary measure before the actual thing happens. So where are we in that actually?
Yes. So, you know, to your points about medicine, I think medicine is just a fantastic application of these ideas, and there's a lot of interest from the medical community. And in fact, I've been talking with a few folks and and participated in a couple of workshops, and it's incredible. It really strikes me how similar aircraft and people are. And, you know, you think about it, you know, what is an aircraft? What is a person? It's a multi-scale, multi-physics system. By the way, fluid dynamics, structural and materials, you know, play a critical role in the human body. It's a field where there are physics-based solvers. So, you know, the finite element models of the heart, the physical models of cancer. But just like an aircraft, you can't possibly simulate everything down to the last molecule, right? You can't simulate at the scale needed to truly resolve things. Just like aircraft, people have long life cycles, and they change over their life cycle. And you would want to be able to, you know, take data and update your models. And then just like an aircraft, you make decisions that are absolutely critical where you have to get them right. So I think at so many levels, I see a lot of analogies between actually medicine and aerospace. And, you know, I think you asked the question, where are we? Again, I think it's, and being predictive. You know, there may be people on the call who know more about the medical space, but from what I've seen and from the people I've talked to, again, it's still at very early days where people are starting to think about to think about something like building a digital twin for a cancer patient. And I think maybe one of the differences there is the use of computational modeling is not as widespread and not as accepted as it is in engineering. that while there has been a lot of a sort of progress in building the computational modeling capabilities, there's still, you know, just sort of as an industry, medicine is very much still a lot focused on experimental and you know, sort of empirical, right? There's a lot of empiricism. So, but then again, because it's an area that's at earlier phases of using predictive models, maybe there's more of an opportunity. So I expect this is something that we will see a lot of advances in the next decade.
Thank you. Thank you.
Yeah. And I would love to have my own digital twin. Would it be great? Wouldn't it be great to tell you, you know what,
yeah.
you should have a healthy breakfast today, because if you don't, you're going to need maintenance next week. So
thank you. Yeah, that'll be wonderful.
We've exceeded time, but if you're okay, we can.
I have time. That's fine. Yes.
Okay. Thanks. Yeah. Priyadarshi, I think Pankaj, you can go ahead.
Yeah. Good evening. A very, very nice and very interesting talk. In aerospace, I'm from working in ISRO, Trivandrum. One thought comes to my mind. We have instrumentation on board our vehicles, be it launch vehicles or aircrafts, based on which we take online decisions, and we provide a very large amount of redundancy for them, so that the decisions are reliable and autonomous systems don't mislead the mission to that is a healthy vehicle not going to failure because of this thing. If we talk about digital twins based on very large set of instrumentation on board machines like UAV, whatever you mentioned, which has large number of components and its trains and other things are to be monitored online, and decisions have to be made. Where do you see that the redundancy issue playing a part? Because for a triple redundant kind of a system, the instrumentation requirements would become so large that it may become untenable. And if there is some subsystem failure, we shouldn't be taking wrong decisions on board based on a digital twin. So that thought comes to my mind. If you have comments on that.
Yes, no, absolutely. That's a great point. And that goes back to the earlier question about whether digital twins should be mandated. And I said, I don't think they're nearly ready enough. So, I mean, this is a real issue, and it's actually a real issue even separate from digital twins, just as there's increased automation and autonomy on board systems, how we ensure that the decision making and the ultimate operation of these systems is at the levels of reliability that we have to ensure when people's lives are at risk. I think, again, there's a lot of academic communities to point to. So people who do, for example, formal methods for verification and for safety has to play a role. And if there's going to be any kind of digital twin that is able to execute onboard decision making on something like an aircraft or a car, those kinds of formal methods have to play a role. I think I personally think that that thinking of the digital twin in a more modular way is also going to be important. That much as like when we built our reduced models, we did it on a component by component basis. I think building the digital twin in more of a modular way where you can manage what goes on in a given subsystem is going to be important for addressing some of those issues again of verification and ultimately determining reliability. And then I think the last thing I would say is, and again, I'll go back to that Apollo 13 example, which is, well, when we say digital twin, I don't know, we imagine something Terminator-like, and it's like the digital twin is driving all the decisions. Maybe that will happen at some point in the future. But in the near term, I think it's more likely that digital twins will help humans make better decisions. And thinking about how the digital twin can complement a human decision maker by bringing information that reflects one particular system that's been dynamically updated And you can think of that both in engineering and also in the medical examples that we were talking about, that the digital twin doesn't have to make the decisions. The digital twin can be the aid, can be bringing more information or better information or more timely information to a human decision maker. So maybe in the short term, the one of the ways that we have to think about that challenge is by thinking about how digital twins work together with humans, and then what that means for how we construct the digital twin and how it communicates information.
Yeah, thank you. That makes it look implementable in real vehicles. Yeah, thank you.
Okay. Any other questions from audience? Okay. If not, let's thank Professor Wilcox for a very interesting talk, and let's hope we will be able to have you on our campus physically sometime.
I'll look forward to that. Thank you. And thank you all for staying late so that you didn't make me get up too early. I appreciate. I know it's well into the evening there.
Yeah, thank you, Karen. I think we hope to see you here after when we have good times.
Very good. Thank you. Thank you, everybody. And thank you for all the great questions.